What is dark matter? Hi, my name's Abby. I'm doing my PhD in atomic and quantum physics, and I'm part of a project developing a quantum sensor to detect ultralight dark matter. Dark matter is proposed to make up 24% of our universe and 80% of all of the matter in our known universe. So why is it called dark? Well, it's because we can't actually see it. The reason we can't see it is because it doesn't really interact with electromagnetic radiation. And electromagnetic radiation is the way that we are able to visualize and see all of the objects in the universe around us. If we can't see it, how do we know it's there? Well, because even though it doesn't emit, absorb, or reflect light itself, what it does do is interact with matter that we can see. So we're able to infer its existence through its interactions with the visible matter in our universe. For example, when we look at galaxy rotations, the material at the center of the galaxies and at the outer edges move in such a way that indicates that the galaxy must contain more mass than we are able to observe. Also, when we look at galaxy clusters, if galaxy clusters only contained the mass that we can see, then that wouldn't be enough to hold them together. They would just fly apart, but they don't, indicating that there must be more mass contained within the cluster than we're able to detect. And one of the most famous indications comes in the form of gravitational lensing. Now, this refers to the way that light bends and distorts around massive objects, and this allows us to estimate how much mass there is in a region. Now remember, it's called dark matter because it doesn't emit, reflect, or absorb electromagnetic radiation in the way that normal matter in the universe does. This means that developing sensors to detect it is very difficult, but it can weakly interact in a way that allows us to develop methods to be able to detect it if it exists. Current mathematical predictions show dark matter to be a spectrum of different types, not just one thing. So on one end of it, you would have heavy dark matter, which would behave more like a particle. Now, this is something you might be able to detect, say, at the Large Hadron Collider at CERN, and you would see it as missing energy in the detectors. On the other end of the spectrum, you would have ultralight dark matter. These are things that are commonly referred to as axions, and they would behave more like a wave. This is something that you could detect in quantum fluctuations of fundamental constants. Now, whether dark matter exists or not, these are exciting candidates and exciting ideas around different ways that we could develop sensors to potentially detect its presence. We just need to figure out where to look for it.